We have a thin metal rod of length capital L and mass M that is resting on two metallic supports as shown on the picture. The rod is not attached to the two supports, it's just resting on the supports. And the supports are connected to a battery and the resistor, and together they're all forming a closed circuit. There's a uniform magnetic field into the plane of the page where the rod is located. And the question is, what is the highest voltage that the battery can have such that the circuit doesn't break at the supports? In other words, what's the highest voltage that the battery can have such that the rod is still in contact with the supports? Let's take a look at the forces acting on the rod. There's gravitational force pulling down. There's normal force from the supports. For simplicity, I'll just put a single normal force on the picture, but there's a normal force from each support. By symmetry, those two forces have the same magnitude and they're both pointing up. They're both supporting the rod upward. Now, how about the magnetic force? The direction of the current in the circuit is counterclockwise, like so. So let's determine the direction of the magnetic force acting on the rod. The formula is I times L cross B, L being the vector that has a magnitude equal to the length of the rod and direction following the direction of the current. So then we're going to do cross product of the current direction and then the magnetic field's direction, right? So if we do L cross B, align your right hand in the direction of the current, which is to the right, horizontal, and then curl your fingers into the page, that's the direction of the magnetic field B. Your thumb is pointing up, so the direction of the magnetic force is pointing up. I have added the magnetic force in my free body diagram as well. So we have three forces: the magnetic force and the normal force pointing upward, the gravitational force is pointing downward. And we're looking for the value of the battery's voltage for which the rod is still in contact with the two supports, meaning if we increase the voltage a little further from that value, then the rod will lose contact with the supports, meaning the normal force will become equal to 0. So basically, we want the voltage value for the battery such that the normal force is equal to 0, that limiting value. As long as the rod is in contact with the two supports, it's in equilibrium. So we apply Newton's first law, net force equals 0, meaning plus F sub B plus F normal minus F sub G is equal to 0. The signs, again, the upward pointing forces are positive and the downward pointing force F sub G is negative. And again, F sub B stands for the magnetic force, F sub N is the normal force, F sub G is the gravitational force. Because we're looking for the maximum voltage that the battery can have, we want the normal force to be equal to 0, so we set this equal to 0. In the next step, I'm going to substitute the defining formulas for F sub B and F sub G. The magnetic force is I times L cross B, and the magnitude of that is I times L times B sine theta, theta being the angle between the orientation of the rod and the magnetic field vector, which is 90 degrees. So we get sine of 90 degrees, which is equal to 1. And the gravitational force is equal to mg, m being the mass of the rod and g is the gravitational acceleration or acceleration due to gravity. Now L is actually the capital L, that's given, the length of the rod. The magnetic field strength is also given, capital B. Mass of the rod is given, m, and g is known. Now what is I, capital I, the current passing through the circuit? Well, it's not given, but we know the battery's voltage. Well, that's what we're looking for, right? We have a single resistor connected to the battery. We ignore the resistance of the wire and the rod. So then by Ohm's law, the current passing through the circuit is simply equal to V divided by R, the battery's voltage divided by the resistor's resistance connected to the battery. So let's go ahead and rewrite our equation again. This lowercase l, that's the general, like this is coming from the general formula, but it stands for, it represents the length of the rod, which in this problem is capital L. So let's rewrite our formula. After substituting for I and rearranging our equation to isolate V, we get V equals mgr divided by L times B. In the follow-up scenario, we do apply the voltage, the maximum voltage that we found in the first part of the problem, but the resistor's resistance drops. And the question is, what is the rod's initial acceleration? Now, why do we talk about acceleration? If you think about it, if for that maximum voltage the resistance drops, what happens to the current? The current will increase, right? If current goes up, the magnetic force will go up, so the magnetic force will exceed the gravitational force, meaning there will be a net force in the upward direction, because there could be no more normal force. Normal force can only be pointing up when the magnetic force is less than the gravitational force. When the magnetic force becomes equal to the gravitational force, that's when the normal force becomes equal to 0. And if the magnetic force exceeds the gravitational force, then there's a net force pointing upward. And by Newton's second law, net force is equal to mass times acceleration. So setting up our force equation for the acceleration version of the problem, we get magnetic force minus gravitational force equals mass times acceleration. We do the same substitution as before for the magnetic force and the gravitational force. And magnetic force is I times L times B, sine theta being equal to 1. I is V over R. This time, the only difference is that, of course, the numerical values are not given in this problem, but this time we have a different value for R, right? That, brings up a different value for the current I. And for F sub G, we substitute mg and rewrite our force equation. We are looking for acceleration this time. We rearrange our equation to solve for acceleration. Just divide both sides by m, and we get acceleration equals v times L times B divided by R times m minus g.